You know, inside every single gadget we own, there's this invisible pulse, a tiny electronic spark. And today, we're going to figure out how on earth we learn to actually measure it.
Think about your phone, your laptop, even the computer in your car. They all rely on one fundamental secret to work properly. And spoiler alert, it has nothing to do with the software.
Nope. It all boils down to the quality of the stuff it's made from, the actual material. But how do you measure the quality of something you can't even see? That, my friends, is the multi-billion-dollar question that engineers have been wrestling with for decades.
Okay, so let's back up a little. Before we can talk about how to measure this spark, we need to agree on what quality even means when you're talking about the teeny tiny world of semiconductors.
And believe it or not, our story kicks off right here. This is a technical report from 1972 from the National Bureau of Standards. This thing was basically the Bible, the first real attempt to create a rulebook for measuring the very heart of these materials.
So the big idea they were chasing is this thing called carrier lifetime. Now stick with me here. The best way to think about it is like this. Imagine every semiconductor has these microscopic, rechargeable batteries inside. When light hits the material, boom, the batteries get charged up. Carrier lifetime is just a fancy way of saying how long does that tiny battery hold its charge. The longer it holds it, the better the material. It's the ultimate quality score.
All right, so how did they actually try to measure this quality score way back in the 70s? Well, the method they came up with was, on paper at least, pretty simple.
Yeah, I know. This setup looks a little intense, but the core idea behind it, called the photoconductive decay method, or PCD for short, is actually really easy to grasp. It's all about a quick flash of light and then watching what happens right after.
So here's the play-by-play. First, you run a little bit of current through a piece of silicon. Then, bam, you blast it with a super short, really intense flash of light. That light just jolts the material, creates a bunch of extra energy, and makes it way more conductive. But the real magic is what you do next. You watch and measure exactly how long it takes for that conductivity to, well, decay back to normal. That amount of time, that was your quality score.
Sounds simple, right? Flash, measure, done. Well, in theory, yeah. But in the real world? Oh, it was an absolute nightmare. That simple test turned out to be a total maze of things that could go wrong. And just look at this list. This is what I mean by a maze. It was just chaos. Literally everything mattered. The temperature in the room, the type of light source, how thick the filter was, how fast the light turned off, even the contacts at the end of the sample. Any one of these things, any tiny little change, could completely wreck the measurement. It can make your final number basically useless.
So what was the result of all that chaos? Get this. The official government report, the one we just saw, admitted that the precision for silicon was plus or minus 135%. Let me say that again. Plus or minus 135%. That's not a measurement. That is a wild stab-in-the-dark guess. Can you imagine trying to build the entire modern electronics industry on a foundation that was basically quicksand?
So yeah, obviously this was not going to work. You can't kickstart a digital revolution when your most basic measurement is that unreliable. There just had to be a better way, right? The industry was screaming for one.
Well, it took a while. For about 20 years, that was the big challenge. And then, finally, a breakthrough.
And here it is, this research paper from 1996. It completely flipped the script. The researchers asked a simple question. What if, instead of that violent, chaotic flash of light, you took a much gentler, more controlled approach? They came up with a new technique, and they called it quasi-steady-state photoconductance. Yeah, it's a mouthful, so we'll just call it QSSPC. So think about it like this. The old method, PCD, that was like setting off a camera flash in a dark room and then trying to figure out what the room looks like from the fading afterglow. It's fast, it's chaotic. But this new QSSPC method, that's like having a dimmer switch. You slowly turn up the light and you watch carefully how the room illuminates at every single level of brightness. By comparing the light going in to the conductivity coming out in real time, this much steadier approach just sidestepped a ton of those problems the old test had. No more guessing from the afterglow.
Okay, so what did this new, clever, steadier method actually get us? Well, to put it simply, it gave scientists a picture with a level of clarity that was it was completely unimaginable before.
Instead of getting one single, probably wrong number, scientists could suddenly see the whole story. Look at this graph from that 96 paper. They could now map out the material's quality score across a huge range of different conditions. This wasn't just an improvement, it was a revolution in what they could actually see.
And why does that matter to you and me? Because when you can measure that precisely, you can build much, much better stuff. This new technique became absolutely essential for developing the super-efficient solar cells we rely on today. And it's a huge reason why the microchips in all our devices just keep getting more powerful and more reliable.
When you step back, this whole story proves a pretty fundamental point, doesn't it? The world we can build is completely limited by the world we can measure. Our ability to create is tied to our ability to see. So it leaves you with a big question. What are we struggling to measure right now? What invisible thing holds the key to the tech of tomorrow?